Good day, students. You had already studied the Coulombs law in our previous lecture. So, according to Coulombs law, the force between two charges Q1 and Q2 is given by F is equals to K Q1 Q2 upon R square, where R square is the separation between the two charges and where K is a constant equals to 1 upon 4 pi epsilon naught, and the value for K is 9 into 10 raised to power 9 Newton meter square per Coulomb square. The units of charges are: number 1, the SI unit of charge is Coulomb. You had already studied it in your 9th class in electricity. So, if Q1 is equals to Q2 is equals to 1 Coulomb and R is equals to 1 meter, then electrostatic force is given by 1 upon 4 pi epsilon naught is equals to 9 into 10 raised to power 9 Newton. The other unit of charge that is in CGS system is stat coulomb. So there is a relation between coulomb and stat coulomb, that is 1 coulomb is equals to 3 into 10 raised to power 9 stat coulomb, or is equals to 3 into 10 raised to power 9 ESU of charge. Now, next topic is Coulombs law in vector form. So, we are having two charges Q1 and Q2. Separation between the charges is R, and two forces are acting on charges. On Q1, force F12 is acting towards the left and F21 on Q2 towards right. F21 force on charge Q2 due to Q1 is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R square, and unit vector R12, where R12 is equals to vector R12 upon the modulus of the vector R, and this is a unit vector. It is directed from Q1 to Q2. Similarly, we are having the force on charge Q1, that is F12 is equals to force on charge Q1 due to Q2 equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R square, and unit vector R21. And again, R21 unit vector is equals to R21 vector divided by the modulus R, and it is directed from Q2 to Q1. The Coulomb force between unlike charges are attractive in nature, whereas between the like charges are repulsive in nature. So in this example, you can see that the Q1 charge is positive, Q2 charge is negative, and the forces are directed inwards, that is towards the center. So this is attractive force, but in previous case the forces were outward along these directions. So what is the importance of studying Coulomb's law in vector form? First importance is, as the distances are equal but the directions are opposite, therefore the unit vector R21 is equals to minus of unit vector R12. Hence we are saying that force F21 on charge Q2 is equal and opposite to the force F12. So the two charges exert equal and opposite force on each other. So Coulombian force obey the Newton's third law of motion, that is, for every action there is equal and opposite reaction. Second importance is, as the forces F12 and F21 acts along the line joining the centers of two charges, so they are central forces. They are acting along the line, so they are central forces. Thank you. After the importance of Coulomb's law, next topic is limitations of Coulomb's law. First limitation of Coulomb's law is the electric charge must be at rest. So the charge should not be in motion. If the charge is in motion, then there is no meaning of studying the charge at rest. That is electrostatics. Second point is the electric charge must be a point charge. So it should be a very small charge, point charge. If it is a bigger charge, it will influence the periphery of the other charge and the property of other charge nearby it. Third, the separation between the charges must be greater than the nuclear size, that is the Fermi size, 10 raised to power minus 15 meter. Otherwise, the strong nuclear forces will dominate over the electrostatic force. You know that the nuclear forces are the strongest forces exist in nature. So they'll dominate and their electrostatic force will become negligible in that case. Next topic is the dielectric constant or the relative permittivity. So what is this relative permittivity? As the name suggests, permittivity is to permit something. So here the permittivity is to permit the influence of one charge on the other. So for two given charges separated by the distance r, we are having two charges q1 and q2 and the distance is r. If the charges are placed in vacuum, then according to Coulomb's law, Coulombian force in vacuum is equals to 1 upon 4 pi epsilon naught q1 q2 upon r square. Mark it as equation number 1. Then Coulombian law, when the charges are placed in medium, in that case, according to Coulomb's law, the force in medium is given by 1 upon 4 pi epsilon q1 q2 upon r square. Mark it as equation number 2, where epsilon is absolute permittivity of a given medium. Now dividing equation 1 by equation 2, we are having force in vacuum divided by the Coulombian force in medium is equals to 1 upon 4 pi epsilon naught q1 q2 upon r square whole divided by 1 upon 4 pi epsilon q1 q2 upon r square. So the common quantities will cancel out and we are having F vacuum upon F medium is equals to epsilon upon epsilon naught, that is epsilon r or k, which is known as the relative permittivity. So this relative permittivity epsilon r is equals to k and is equals to epsilon upon epsilon naught. The value of relative permittivity in vacuum is 1. In air is 1.00054. In water is 80. So after these topics, let us solve few numerical problems, and the formulae used to solve the numericals are Coulomb's law in vacuum, that is force in vacuum is equals to 1 upon 4 pi epsilon naught q1 q2 upon r square. Force in medium is equals to 1 upon 4 pi epsilon q1 q2 upon r square, where k is equals to 1 upon 4 pi epsilon naught is equals to 9 into 10 raised to power 9 Newton meter square per Coulomb square. and the charges are in Coulomb, distance is in meter, and force is in Newton. So the first numerical problem is the electrostatic force of a repulsion between two positively charged ions carrying equal charges is 3.7 into 10 raised to power 9 Newton when they are separated by a distance of 5 angstrom. How many electrons are missing from each ion? So, before solving this, let us first collect the terms which are given in this numerical problem. So, the force is given 3.7 into 10 raised to power minus 9 Newton. Distance is 5 angstrom, that is 5 into 10 raised to power minus 10 meter. Let the charges are Q1 is equals to Q2 is equals to Q. Applying the Coulombs law, force is given by 1 upon 4 pi epsilon naught Q1 Q2 upon R square. Therefore, after substituting the values, we are having Q is equals to 3.2 into 10 raised to power minus 19 Coulomb. Also, according to the quantization of charge property, we are having the formula Q is equals to plus minus NE, and substituting the values, the number of charged particles are given by Q upon E, and that is N is equals to 2. Hence, 2 electrons are missing from each ion. So students, our second numerical problem is 2 point charges of charge capital Q and small q are placed at distance x and x by 2 respectively from a third charge of charge value 4q. All charges being in the same straight line, calculate the magnitude and nature of charge q such that the net force experienced by the charge q is 0. So let us first draw the figure for the given problem. We are having the charges capital Q, small q and 4q. So as per the problem, the q is at a distance x from 4q and small q is at a distance x by 2 from 4q. It is given in the problem that the force experienced by this q because of this and this is 0. That is, the system is in equilibrium. So, for the equilibrium of charge q, the charge capital Q must have the same sign as that of small q or 4q. Hence, the force Fa due to force charge 4q and charge capital Q must be equal and opposite. That is, Fa and Fb should be equal. So, applying the Coulomb's formula, that is 1 upon 4 pi epsilon naught, charges are here 4q and q, 4q and q, divided by the separation between the charges, that is x by 2 whole square. Similarly, force due to charge capital Q is 1 upon 4 pi epsilon naught charge Q, capital Q and the separation between the charges square. Cancelling the term, we are having capital Q is equals to 4Q, or the two charges are equal in magnitude. Now, there are two numerical problems for your practice. Number 1, obtain the dimensional formula of epsilon naught, and you had studied in your 11th class how to calculate the dimensional formula. Second problem is calculate Coulomb's force between two alpha particles separated by distance of 3.2 into 10 raised to power minus 15 meter in air. So distance is given, charge on alpha particle is plus 2q. After substituting the values in Coulomb's law, you can easily find out the solution. So students, after the Coulomb's law, next topic in electrostatics is the superposition principle. As the name suggests, superimpose, and you had already studied this superposition principle in your 11th class, that is in chapter waves, where the waves were superimposed in order to get the resultant wave. So the superposition principle is forces between multiple charges. According to superposition principle, when a number of charges are interacting, the total force on given charge is the vector sum of the forces exerted on it due to all other charges. The force between two charges is not affected by the presence of other charges. In order to understand this, let us consider a system in which we are having n number of charges placed in vacuum, and R1, R2 till Rn are their respective position vectors from origin. So according to superposition principle, the total force on a given charge Q1 will be the sum of all the forces on this charge because of the other charges. So here in this figure, we are having this charge plus Q at this position, another charge Q3 at this position, and the charge Q2 at this position. This charge Q1 is at a distance R1 from origin. Charge 3 is distance R3 from origin, and similarly charge Q2 is at a distance R2 from the origin. So these charges are influencing this given charge Q1, and the force experienced by this charge Q1 due to Q3 is F13, and force experienced by this charge due to this Q2 is F12. And these are vector quantities. So we need to find out the resultant, and the resultant force F1 is along this direction. Now, according to Coulomb's law, the force exerted on charge Q1 due to Q2 is F12 vector is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R12 square and R12 unit vector. In vector notation, it is 1 upon 4 pi epsilon naught Q1 Q2 R1 vector minus R2, that is the resultant, square, and the unit vector is vector upon the modulus of vector, and it is given by 1 upon 4 pi epsilon naught Q1 Q2 vector R1 minus vector R2 divided by R1 minus R2 modulus Q, where unit vector R12 is equals to vector R1 minus R2 divided by the modulus of vector R1 minus R2. This is a unit vector pointing from Q1 to Q1 and Q2 to Q1, and R12 is vector R1 minus vector R2. Hence, the total force on charge Q will be the sum of all the forces. So that is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R12 square R12 vector plus Q1 Q3 upon R13 square R13 unit vector, and so on till Q1 Qn upon R square R1n square and R1n unit vector, or F1 is equals to Q upon 4 pi epsilon naught summation I is equals to 2 to n Qi divided by R1I square R1I unit vector. So here I vary from 2 to n. In terms of position vector, again we can write it as F1 is equals to 1 upon 4 pi epsilon naught Q1 Q2 R1 vector minus R2 vector divided by R1 minus R2 Q, and so on till the force by charge n. And writing in summation form, F1 vector is Q upon 4 pi epsilon naught summation I is equals to 2 to n Qi Ri R1 minus Ri divided by R1 minus Ri Q. So if we are using the notation as this is charge or charge particle A, so in that case this will be the resultant force acting on this charge due to the other charges. So the net force in whole system will be Q upon 4 pi epsilon naught summation all point charges Q dash R minus R dash vector R minus R dash vector whole cube modulus. There is a numerical problem. Now, an infinite number of charges, each equal to 4 microcoulomb, are placed along x-axis at these distances. Find the total charge. So, after finding the values, applying the Coulombs law and putting the values here, the distances are varying. So, substituting the values, this is a GP, and you know that the solution for GP is A upon 1 minus R. So, A is your first number and R is the difference between these. So, this value is 4 by 3 after solving this, and the net resultant force is 4.8 into 10 raised to power 4 Newton. After superposition principle, our next topic is electric field. As the name suggests, field of electricity or the charge. So, as you know that what is a field, in chapter magnetic field in your 10th class, you had studied that the magnetic field is area around the magnet where the magnetic influence can be experienced. Similarly, for a given charge, electric field is the area or periphery around that charge where the influence of a given charge can be experienced by another charge. So, here we are having a source charge Q at position O. This is a positive charge, and another test charge, which is also a positive charge, is placed at position P. Now, we will find out that this test charge is influenced by this source charge. So there is a electric field of this charge which is influencing or exerting a force F on this test charge Q naught. Hence, the electric field is said to exist at a point if a force of electrical origin is exerted on a stationary charged body placed at that point without disturbing the position of source charge. So this is our test charge and this is our source charge. So the electric field experienced by this test charge is E is equals to the force of this charge divided by the test charge. This point is to be noted that the direction of electric field is same as that of the force F exerted on the positive test charge. So the direction of electric field of this charge is along the force exerted on this test charge because of this given source charge. Units and dimensions of electric field. SI unit of electric field is Newton per Coulomb, which is equivalent to volt per meter. Why it is Newton per Coulomb? Because electric field is equals to force upon charge. Unit of force is Newton and unit of charge is Coulomb. Hence, the unit of electric field is Newton per Coulomb. Dimensions for electric field are field is equals to force upon charge is equals to dimensions for force are mlt minus 2 and for charge it is Coulomb. Hence the dimensional formula for electric field is mlt minus 3 a minus 1 where a is in ampere. So let us solve a numerical problem based on electric field. Calculate the voltage needed to balance on oil drop carrying 10 electrons when located between the plates of a capacitor which are 5 mm apart. The mass of oil drop is 3 into 10 raised to power minus 16 kg given G is equals to 10 meter per second square. Here these are the given quantities. At the highest point, we know that the particle comes to rest for a fraction of second. So here the upward force on oil drop due to the electric field is equals to weight of oil drop. So equating the terms, this is the force due to electric field E on charge Q, that is equals to mass of charge divided by mass of oil drop divided by the weight, acceleration due to gravity, sorry. So substituting the values, we know that field is equals to potential upon the distance. After substituting the respective values, the potential on oil drop is 9.375 volt. Now, there are two numerical problems for your practice. Number one, calculate the electric field strength which can just balance a deuteron of mass 3.2 into 10 raised to power minus 27 kg given G is equals to 10 meter per second square. Second, calculate the electric field strength required to just support a water drop of mass 10 raised to power minus 3 and having a charge 1.6 into 10 raised to power minus 19 Coulomb. Apply the same formula Q is E is equals to mg. You will find out the result. So students, after having the conceptual idea of electric field, let us find out the electric field due to a point charge. So we are having a source charge Q at position O and a test charge at position P, and the distance between the two charges is R. The force F on test charge Q naught due to source charge Q is given by, according to Coulomb's law, F vector is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R square and the unit vector R, where the unit vector is in the direction from Q to Q naught. And we know that the electric field for a given charge is force divided by that charge. So here the electric field experienced by this charge Q naught is F upon Q naught is equals to 1 upon 4 pi epsilon naught Q upon R square into unit vector R. The magnitude of electric field is E is equals to 1 upon 4 pi epsilon naught Q upon R square. So from this relation we conclude that E field is proportional to 1 upon R square, and after plotting this electric field along y-axis and the distance along the x-axis, we are having this exponential curve. E is proportional to 1 upon R square. Hence, we conclude that such a field is a spherical symmetric or a radial field. After finding out the electric field due to a point charge, let us find out the electric field due to system of point charges. So here in this figure we are having a system of charges and a test charge Q naught is at position P, where we want to find out the total electric field experienced by this test charge Q naught due to the other charges. So we are considering the charges Q1, Q2 till Qn, that is n point charges. Their respective position vectors are R1, R2 till Rn from the origin O. So from this arrangement, we are having a test charge Q naught at position P, whose position vector is R vector from origin. One charge is at this position, distance R1 vector from O, and Q2 charge is at this position, distance vector R2 from O origin. These two charges exert force on this test charge, and hence the field of these charges influence this charge, and the net electric field experienced by this test charge is the resultant of these electric field vectors along this direction, that is E1 plus E2. So according to Coulomb's law, the force on charge Q naught due to Q1 is F1 vector is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R1p square and R1p unit vector. Therefore, the electric field at point P due to charge Q1 is E1 is equals to F1 upon Q naught is equals to 1 upon 4 pi epsilon naught Q1 divided by R1p square R1p unit vector. So this is the field because of charge Q1. Similarly, the field because of charge Q2 is 1 upon 4 pi epsilon naught Q2 upon R2p square R2p unit vector. Applying the superposition principle to find out the total electric field, we are having E is equals to E1 vector plus E2 vector plus so on till En vector, or the total electric field E vector is equals to the constant quantity 1 upon 4 pi epsilon naught summation I is equals to 1 to n qi divided by RIP square, and RIP unit vector.